Now, when you compare the size of the nucleus to the size of the atom, the size of the nucleus, as you can see here, it's something times 10 to the power minus 13 centimeter, which is 10 to the power minus 15 meters, while the size of the atom is something times 10 to the power minus 8 centimeter, which is 10 to the power minus 10 meters. If you divide these two numbers, you will find that the ratio is approximately 1 to 100,000, which means the atom is bigger than its nucleus by 100,000 times. To show you the big difference between these sizes, the big difference in size between the nucleus and atom, assume that you are sitting in the center of Riyadh city. This is a Riyadh city. Riyadh, including all villages and all towns around Riyadh. Let's say it has a circular shape. This is a Riyadh city with a diameter from far west to far east with about 100 kilometers. 100 kilometers, it's 100,000 meters. And you are sitting here in the center of Riyadh city. You and your table has a diameter of 1 meter. So when you compare the size between you and your disk to the size of the Riyadh city, it will be approximately the same as the ratio between the size of a nucleus and the size of the atom. There is a big difference between them. This table here summarizes two basic properties of protons, electrons, and neutrons, which are the charge and the mass. The first, or each one of them, is given by two values, the relative value and the absolute value. So here we have relative charge and absolute charge. Same thing for mass. We have relative mass and absolute mass. Now, what's the difference between relative value and absolute value for any physical quantity? Simply, the relative, it doesn't represent the actual values. Yani, for example, when I say I got double the mark, or my mark is double the mark of my friend. So I got the double of his mark, twice his mark. So when you compare the ratio between my mark to his mark in the exam, it will be 1 to 2. But it doesn't mean I got 1 and he got 2. This is not the actual marks. If the exam is marked out of 100, then if my mark is 100, then his mark will be 50. If my mark is 60, his mark is 30. 60, 30, 150, these are the actual marks that we got in the exam. So these are called absolute values. While 1 to 2, this is just a comparison between my mark to his mark, or my grade to his grade, which is a relative. So here, if we compare the absolute proton, or the absolute charge of proton, we'll find it that plus 1.6 times 10 to the power minus 19 coulomb. For a neutron, because it doesn't have any charge, it's 0. While for electron is minus 1.6 times 10 to the power minus 19 coulomb. These are the actual or the absolute charges of protons, electrons, and neutrons. When we divide these two numbers to get the ratio or the relative values, we will find that the charge of a proton and electrons, they have the same magnitude with opposite sign or opposite charge. So if the proton is given by a charge of the charge of a proton is given as +1, then definitely the charge of electron will be -1. +1 and -1. These are the comparison between them, which are the relative charges. Which is more important in chemistry? The relative or the absolute charges? Actually, both of them are important, but in this course, because it's an introductory course, we'll focus more on the relative charges compared to the absolute charges. So from this moment, you should realize that the proton has a charge of a +1, neutron 0, while electron is -1, +1 and -1. These are the relative charges, not the actual or the absolute charges. Same thing for mass. The absolute or the actual mass of a proton is 1.672 times 10 to the power minus 24 grams, which is a part of a trillion of the gram. It's extremely small. It's almost almost something that we cannot imagine. Very, very small. The mass of a neutron is 1.674 times 10 to the power minus 24 grams. Approximately, the mass of a proton and a neutron are equal. Little bit, the neutron is heavier than the proton, while the mass of electron is 9.1 times 10 to the power minus 28 grams. So if you compare these three masses together to get the relative masses, you will find that the mass of a proton is 1.007, a neutron 1.008. Let's ignore these fractions. Let's say the relative mass of a proton is 1, the relative mass of a neutron is also 1, while the relative mass of electron is 0.0005. It's very small compared with the mass of a proton or a neutron. Actually, if you divide the mass of a proton over the mass of electron, you will find that for each 1,800, about 1,800, 1,700, something like this, the mass of one proton equal the mass of 1,700 or 800 electrons together. And as we don't have this number of electrons in any atom, then we can say the maximum number of electrons is 118. So here we can say that the mass of electrons is negligible. You can ignore the mass compared with the mass of protons and neutrons. Now go back to the atomic structure here. Here, as we said, we have a nucleus in which you can find the protons and the neutrons, and electrons around the nucleus rotate outside the nucleus. As the heavy components of the atom, which are protons and the neutrons, are allocated in the nucleus, then we can say that the entire mass of the atom comes from the nucleus, because the outside the nucleus you can find nothing. You can find only the space and electrons. And because the mass of electrons is negligible, so the entire mass of any atom comes from its nucleus. Keep this information in your mind. Now the next point is the isotopes, ions, and the periodic table. Here we have a sample of periodic table. In periodic table, you can get three fundamental information about any atom. We mentioned previously that all known atoms, which are the simplest building block for any element or for any matter in general, is atoms, and these atoms are arranged in periodic table. Here we have a sample of periodic table. The first information that you can obtain from the periodic table is X, where X is the atomic symbol here. It's the abbreviation of the atomic symbol. For example, if X is C, then this is carbon, and A is sodium, H hydrogen, O oxygen, and so on. Now, you can also find two numbers associated with each one, with each atomic symbol, which are what? Which are the, here is Z, and here is A. The lower number and the upper number, they are listed here in the left corners, in the left upper corner and in the left lower corner. One of these numbers is called the atomic mass, atomic number, sorry, and the other number is called the mass number. The atomic number is the number of protons. This is very important number because it's similar to your fingerprint. For all atoms of the same type, this number of proton is constant. You cannot change it. If you change the number of protons, then you will change the type of atom. So for all carbon atoms in the universe, the atomic number is 6. And for all oxygen atoms in the universe, the atomic number is 8. They have a fixed number of protons. You cannot change it. If the number is changed from 6 to 7, for example, then you will change the type of atom. You will change it from carbon to nitrogen. Nitrogen 7. If you change it to 8, then you will get oxygen, and so on. The other number is called the mass number, which is here the upper number. The mass number, as we said, what are the particles that important to get the mass of any atom? Yes, the answer is protons and neutrons. So simply, the mass number is the number of protons and neutrons, while electrons is negligible. You can ignore it. Now, let's study these three numbers, the number of protons, electrons, and neutrons, and let's discuss which one of these numbers is constant and which one is variable. So here within the same type of elements or atoms, to be more precise, let's say atoms. The number of protons, as we said, is constant. This has a fixed and a constant value. You cannot change it. While the number of neutrons in the same type of atoms, this number, it can be variable. What does it mean? It means that I can find two same atoms, same type of atoms, yani same number of protons, with different number of neutrons. Such type of atoms are called isotopes. Isotopes. So isotopes are atoms of the same type, which means same number of protons, but different number of neutrons. Now, when you change number of neutrons, then definitely the mass number will be changed. So we can define isotopes as atoms of the same type, but with different mass number or different number of neutrons. The third number is the number of electrons. By the way, this sign is number. I always use it for number. Number of atoms, number of moles, number of electrons, so on. Number of electrons is also variable. I can find two atoms that have the same type, two oxygen atoms, two nitrogen atoms, two sodium atoms, etc., but with different number of electrons. Such atoms are called isotopes. Are called ions. We call them ions. Now, electrons, as we said, have negligible mass, but they have considerable charge. So if the atom contains the same number of protons and electrons, the protons equals electrons, then this atom will be neutral. Now, if the atoms or if any atom contains more or less number of electrons compared with the protons, then we'll form ions. So what are the possible type of ions? The answer is you can form positive ion or negative ion. In positive ions, the number of protons should exceed the number of electrons. They contain more protons compared to electrons, while in negative ions, the number of protons is less than the number of electrons. Now my question is, how can we form ions? As in ions, there are different number of electrons and the protons. How can we form these ions? By increasing or decreasing the number of protons or the electrons? Yes, you are right. By increasing or decreasing the number of electrons, because again, ions are formed with the same type. We are discussing the ions of the same type of atoms, which means the number of protons is fixed. It has a fixed value. We cannot change it. Here we have an example of isotopes. Look here. Here we have two sodium atoms, this atom and this atom here. Both are sodium. Both contain the same number of protons, which is 11 and 11 here. What's the difference between them? The difference is the mass number. The first atom contains 23. The mass number of the first atom is 23, while it's 24 for the second atom. Now, if you determine the number of protons for this atom, it's 11, which is the mass number. The number of electrons is also 11. Why 11? Because as you can see here, this atom is neutral. If the atom is charged, and if we have any ion, then the charge is always written here in the upper right corner. If you can find nothing in this place, then you can say that this atom or this molecule is neutral. What's the meaning of a neutral? A neutral means it doesn't carry positive or negative charge. Now, here we already know that it contains 11 protons. 11 protons, يعني 11 positive charges. So how can we make the charge neutral? How many negative charges we need to neutralize the 11 positive charges of protons? The answer is 11. 11 negative charges, which means 11 electrons. How many neutrons? We said that the mass number, which is the upper number, equal the number of protons plus neutrons. Now this mass number is 24, or here is 23 for the first, minus 11. So this equals 12. And for the second, it will be 13. So why these are isotopes? Because they are atoms of the same type. Both are sodium. Both have the same protons or same number of protons, but different mass numbers. Check this example here. Determine the number of protons, neutrons, and electrons for each of these. Sulfur 1632, sulfur 1632 minus 2, sulfur, and so on. Number of protons in the first one, which is sulfur 1632, is 16. And this is neutral. We don't have anything written here in the upper right corner. So it contains again 16 electrons, while the neutrons is 32 minus 16, which is 16. We forgot to tell you that the positive and negative ions here, we said that we can form positive or negative ion. Positive ions are called cations and negative ions are called anions. It's just a detail that you should know. Now go back to our example. Here is the problem. So this contains 16 protons, 16 electrons, and 16 neutrons. Same element, same atom, but we have a charge of minus 2. Here, the charge is minus 2. So the number of protons is 16. The number of neutrons, again, 32 minus 16 is 16. So how many, now this carries a negative charge. It's sulfur minus 2. This is an ion, a negative ion. As the charge is minus 2, it means that this atom contains two more electrons compared to protons. Because and as the protons is 16, then the electrons, it should be 18. Why 18? Again, because the charge is minus 2. So the negative charges, which are the charges of electrons, is more than the positive charges, which is the charge of proton by 2. It means I need two more electrons to make the charge minus 2. Sulfur plus 1, the third one here. Sulfur plus 1, everything is the same except the charge. Plus 1 means the number of protons which are positive is greater than the number of electrons which are negative by 1. This is why the charge here is plus 1. So as sulfur contains 16 protons, then it must contain 15 electrons to make the charge plus 1. Sulfur minus 2 and sulfur plus 1, these are called ions because they are atoms of the same type but with different number of electrons as we explained previously. Now, uranium 92-235 and uranium 92-238. As you can see here, these two atoms are similar in everything except the mass number. So what we call them? These atoms are called isotopes. This is why we call them isotopes. 92 means 92 protons. Number of neutrons, subtract the mass number minus the number of neutrons, it will be 143, while the number of electrons is again 92 because this is a neutron. And for 238, the number of neutrons is 146. This is the only difference between them. So they are isotopes. This is how to determine the number of protons, electrons, and neutrons for any given species. Let's solve this example together. A certain isotope, X, contains 23 protons and 28 neutrons. What's the mass number of this isotope? Very simple and very easy. As you know, the mass number is the number of protons plus neutrons. Both are given. Protons is 23 and the neutrons 28. So the answer is 51. Identify the element. The second part of the question asks you to identify the element. To identify the element, you should go to periodic table and check which element in periodic table contains 23 protons. You should always check with the number of protons because, as we said, this is the fingerprint This is the characteristic number of each atom. The answer is vanadium. When you go to periodic table, you will find that vanadium has the atomic number of 23. Another example, a certain isotope X plus 1 contains 54 electrons. What's the mass number of this isotope? Now you know that the mass number is protons plus the number of neutrons. The number of neutrons is given, it's 78. The number of neutrons is 78. So to determine the number of, or the mass number, we have to determine the number of protons. Now the charge is +1, and the question gave me the number of electrons. What does it mean when the charge is +1? Which is greater than the other? Protons is greater than electrons, or number of electrons is greater than protons? Yes, you are right. The number of protons which are positive is greater than number of electrons. By what? By 1, because the charge is +1. If the charge is +2, then it will be greater by 2 or 3 or 4 or according to the value of the charge. So here +1 means we have one more proton compared to electrons. So we have 55 protons and 78 neutrons. So the answer is 133. Identify the element, go to periodic table and check which element in periodic table has the atomic number of 55. Here is the periodic table. It's very important to understand how atoms are arranged in periodic table. As you can see here, periodic table consists of columns. These columns are called groups, and rows or lines, horizontal lines. These lines are called periods. Atoms are arranged in the same group according to the similarities in their chemical and physical properties. So we expect that, let's say here the last column, helium, neon, argon, krypton, xenon, and so on. These are called noble gases. They are similar to each other in their chemical and physical property. This is the criteria behind the arrangement of atoms in the same group. While atoms are arranged in periods or rows, horizontal lines from left to the right, it's just a serial arrangement of the atomic number. We start with hydrogen here, which is 1, then 2, helium, then go back 3, 4, 5, 6, 7, 8, 9, 10, and so on. By the way, you can find here the upper number is the atomic number, while in the previous example, the lower number was the atomic number. What does it mean? It means that this arrangement is not important. In some periodic table, the atomic number is listed at the upper number, while in other periodic table, you can find it at the lower number. So how can you distinguish between atomic and mass number? Very simple. The smallest number is the atomic number, and the bigger number is the mass number. The smallest is the atomic, and the bigger is the atomic number. So the criteria behind the arrangement of atoms in the same period is just a serial arrangement according to the atomic number. The next point in periodic table. The next point is the colors of this periodic table. We can see that it has different colors. But before the colors, the next point is the types of elements. In periodic table, we have two major types of elements, which are group A elements. The first group here, this is 1A. The second column is 2A. 3A is not here. 3A, you can jump over this zone in the middle. Jump here. This is a 3A. Then 4A, 5A, 6A, 7A, and 8A. So we have 8A group elements. These are called group A elements or main group elements. Don't forget it. Elements in the left and in the right, these are called group A elements or main group elements. While those elements in the middle here, these are called the transition elements or group B elements. This is why the number of each column is B. It has a B letter. Okay. Now the third point is the colors in periodic table. We have 4 different colors. The yellow color in the right, then the gray color here in the middle. Then in the left side of the periodic table, you can find blue color, 2 degrees of blue color, the dark blue color and the light blue color. All elements in blue, dark blue here and here, here and here, this is the dark blue. These are called metals. And the light blue, here in the middle, these are also metals, but they are called the transition elements or transition metals. So again, all elements in blue are metals. We have two types of metals, the main group metals in the left and in the right, which are related or belong to group A, and the transition metals, which are here in the mid zone or in the area here. These are the transition metals. All elements in yellow are called non-metals. Those elements in yellow are non-metals. In between, we can find 1, 2, 3, 4, 5, 6. These green metals, green elements are called metalloids. Now, what's the difference between metals, non-metals, and metalloids? Actually, the main difference between them is the conductivity, the heat conductivity. All metals are good conductor of heat and electricity. All non-metals are poor, very poor conductors or non-conductors of heat and electricity, while these 6 metalloids, they have moderate characters, they have some characters in between. Their conductivity is moderate between metals and non-metals. In the exam or in the problems, most of periodic tables are non-colored. You will not be given these colors. So as these colors are not given, then you should distinguish between these different classifications by yourself. My advice is just to memorize these 6 metalloids. To the right of them, you can find the non-metals. To the left of them, you can find metals, and I think it's very easy to distinguish between metals and non-metals. Last point is the names of the group. Some groups or columns in periodic table, some of them have characteristic names. For example, group 1A, this is called alkali metals, this group here, except hydrogen. Hydrogen, by the way, this is an exception. An exception. It's written with metals, even though it's a non-metal. This is why we put it here in a yellow color. Why we put it with the group 1A, which are alkali metals? Because the atomic number of hydrogen is 1. This is why we should start with it. And by the way, in many versions of periodic table, you can find hydrogen written separately somewhere here or there. Okay, so hydrogen is non-metal, but it's listed with a group 1A, which is alkali metal. A group 2A, also it has a characteristic name, which is alkaline earth metal. This is also important, alkaline earth metal. A group 7A, these are the halogens, and a group 8A, this is noble gases. Noble gases are among the most important groups in periodic table. I'll give you this information, which is very useful later. Inshallah, we'll go back to this information later. Noble gases are very, very important gases and very important elements due to a characteristic properties of them. These noble gases are inert. Inert means inreactive. They don't react with other elements. They are stable by themselves, extremely stable. Why they are stable? Later in chapter 7, we'll discover that this atomic number, which is number of protons or number of electrons, because in periodic table, all atoms are neutral. They contain the same number of protons and electrons. All of them are neutral. They don't carry any charge. So the number of protons in periodic table equal the number of electrons. Later in chapter 7, we'll discover that these number of electrons in periodic table are sufficient to fully fill their valence shell orbitals. Valence shell orbitals are fully filled with electrons, which means there is no need for them to react with any other element to find the lack or to fill the lack of electrons. They already have a full valency, a full valence orbitals. We'll discuss all these details in all these points in details in chapter 7. While all other elements in periodic table, they don't have this character. Some of them have more electrons than their orbital need or less electrons than their orbital need, so they will try to be stable in similar manner to the noble gases. here are the details that I already explained. You can find them written here. Okay. Metals are good conductors of heat and electricity. Non-metals, poor conductor. Metalloids, they have intermediate or moderate characters. Alkali metals are those in group 1A, alkaline in group 2A, halogens in group 7A, and noble gases in group 8A. This is in general how atomic number or how atoms are arranged in periodic table. Now let's move to the next topic, which is very important. The chemical bonds. How atoms are combined with each other and how these ions or how these atoms can form the chemical bonds. The answer is by two different type of bonds. The first one is called the ionic bond and the second one is called the covalent bond. In ionic bond, you should have a metal combine with another non-metal metal from the blue zone, regardless whether it's main group or a transition, with a non-metal from the yellow zone. Okay. While in covalent bonds, you will have a non-metal combined with another non-metal. This is the first point to distinguish between them. In ionic bond, from the name, ionic from ions. Ions means positive and negative charges. Then here I expect to form positive charge with negative charge because positive with negative and attraction will take place between them, which is a bond. So you can combine or bind the atoms by forming positive and negative charges. Now the question is, which will form the positive ion and which will form the negative ion? The answer is the metal will form the positive. It will lose. All metals prefer to lose X number of electrons because when we compare the number of electrons of these metals with the number of electrons with their corresponding noble gas, we will find that they have more electrons compared to the noble gas. So they will try to lose this excess number of electrons. When they lose it, then they'll form a positive charge, positive X, where X is the number of electrons lost. Non-metals, when we study them, we'll find that they contain less electrons than they need compared to the corresponding noble gas. So they will try to gain electrons. If the non-metal gains 1 electron, then it will form -1. The charge of the anion is -1. If it gains 2 electrons, then it will be -2. Y electrons in general, it will form -2 electrons. So here, the metal will be plus X and the non-metal will be -Y. Once you determine the charge of the metal and the charge of the non-metal, to combine them, what shall you do? You have to take the charge of the metal and make it subscript of the non-metal, and the charge of the non-metal make it subscript of the metal. So you will form My. Here, when you write the subscript, make sure that all subscripts are positive because these subscripts, they represent the proportion or the ratio in numbers. So these numbers are always positive. So take the absolute value of -y. -y, it's y, and here in x. For example, if I have a metal, if I have a metal with a charge of +4 and non-metal with a charge of -2, then when I combine them with each other, I will form M2N4. Last step, simplify this ratio. Ask yourself, can I simplify the ratio, these subscripts, using whole number? If you can, you should do. So here, when you simplify it, it will be M1N2. The 1 is not written. While if you combine M plus 3 with N minus 2, M plus 3 with N minus 2, do the same, make this a switch, you will get M2N3. Can you simplify in M2N3? No, you cannot simplify it. So this will be the final formula of the resulted compound. This is how the ionic bonds are formed. This is how ionic bonds are formed. After the simplification, here we write simplify if possible. After the simplification, you will get the simplest ratio between y and x. This is called empirical formula. Inshallah, we'll later discuss the empirical formula, but keep in mind empirical formula is the formula in which you have the simplest ratio between the molecules. Now, covalent bonds. In covalent bonds, as we said, you should have a nonmetal with another nonmetal. You don't have losing or gaining of electrons in covalent bonds, similar to ionic bonds. In ionic bonds, we have losing and gaining. Metals will lose, and non-metal will gain electrons. So losing, gaining. While in non-metal and non-metal in covalent bonds, we don't have losing or gaining. We have sharing of electrons. And we call the resulted compounds molecules. We call it molecules. And in chapter number 8, we'll study these covalent bonds in details in chapter 8, inshallah. Now, the most important, here in chapter 2, we'll focus on ionic bonds and how they are formed. Here is the periodic table again. The most important point in ionic bond is to determine how many electrons should be lost by the metal and how many electrons should be gained by the non-metal. Yani in short, you should find the value of x and the value of y. The question is how. The answer is by going to periodic table. When you compare in periodic table, here is the noble gases. Can you see the noble gases? It's here. These are the noble gases, group 8A. Simply compare the number of electrons that you have for your element with the number of electrons for something called corresponding noble gas. Corresponding noble gas is the closer and lower noble gas compared to your element. What I mean by that? I'll give you an example. Right? The formula of the ionic compound, sorry, the ionic compounds that will result from the following combinations. Let's say the simplest example, sodium and chlorine. We always need to keep the noble gases in front of us because they are our reference. The first noble gas is helium with 2. The second one is neon 10. The third one is argon 18. The third one is krypton 36 and xenon 54 and so on. Sodium has the mass number or the atomic number of 11, where chlorine is 17. Now, as we said, the noble gases are stable, and all other elements in periodic table, they will try to be stable in a similar manner to these noble gases, so they will try to have the same number of their electrons. But not any number. You should compare each atom by the corresponding noble gas. Corresponding noble gas is the noble gas from this list that is closer to the atomic number to the element of interest. Here, sodium is the element of interest. It has 11 electrons or 11 protons. Where is the corresponding noble gas from the list? Where is the closer noble gas to sodium? Yes, the answer is neon. Neon has 10 electrons. So for sodium with 11 electrons to be similar to neon with 10 electrons, what should happen to sodium? Yes, you are right. It should lose 1 electron. When the sodium atom lost this electron, the charge of sodium will be +1 because it will end with 11 protons and 10 electrons, as one of these electrons is lost. So here the charge is +1. Do the same for chlorine. Chlorine is 17. Where is the corresponding noble gas from the list? Yes, the answer is argon, argon 18. For chlorine to be similar to argon with 18, then it should gain 1 electron to form Cl-1. So this is the most important step. After that, I think it will be very easy. Now to write the resulted compound from this combination, just take the charge of sodium, make it subscript of chlorine, the charge of chlorine, make it subscript of sodium, then it will be Na1, L1 is not written, and Cl1, sorry, 1 is not written again. Can we simplify this ratio? The answer is no, we cannot simplify 1 to 1. So this is the final answer of Na of this compound. It's NaCl. Let's take another example. If we have magnesium with, let's say, with sulfur. Magnesium is 12, sulfur is 16. Where is the corresponding noble gas of magnesium? The answer is neon again here. Neon is the closest noble gas to magnesium. Neon is 10, magnesium is 12. Then magnesium will lose 2 electrons. It will lose 2 electrons to form Mg minus 2 or plus 2. Yes, it's a plus 2. Sulfur is 16. The corresponding noble gas is argon 18. So sulfur will try to gain 2 electrons to form S minus 2. Now combine them. Make charge subscript, you will get Mg2 S2. Is it the final answer? No, it's not the final answer. Why? Because the final step is the simplification. Can you simplify 2 and 2? Yes, we can simplify them to get Mgs. So this is the formula, the empirical formula of magnesium sulfide. This is how ionic bonds are formed. I hope it's clear. Now, based on these information, we can proceed to the last topic of this chapter, which is naming simple chemical compounds. To name chemical compounds, we can distinguish between the ionic type and the covalent type compounds. If the bond is ionic, which means you have here metal with non-metal, then you will be here. You will be in type 1, type 2, and type 3. So type 1, 2, 3 all belong to the ionic compounds, while type 4 is related to the covalent compounds in which you have non-metal with another non-metal. Now, the objective of this section is the naming chemical compounds. As you know, chemical compounds are thousands. We have a huge number of chemical compounds. So it doesn't make sense to memorize the names. So the thing that we'll follow is we will define a certain naming procedure for each type. The first step is to classify the given example, whether it's type 1, 2, 3, or 4. After that, you can follow the procedure that is related to each type. Type 1, 2, 3, again, all of them are ionic. What's the difference between them? In type 1 here, the metal should be main group metal from group A with a non-metal. Type 2, the metal is a transition metal with non-metal from group B. While in type 3, you will have a metal regardless whether it's main group or transition. Both are acceptable here in type 3. Main group or transition, it doesn't matter. With something called polyatomic ion. What we mean by polyatomic ion, we'll inshallah explain it later. Type 4, this is very different because in type 4 you have a non-metal with another non-metal. So now I will go through the naming procedure of each type of them with 1 or 2 examples to end the chapter. Now let's start with type 1. This is type 1. As we said in type 1, you should have a main group metal with a non-metal. The naming procedure, the steps are as follows. Write the name of the main group metal as it is, don't change it, followed by the name of the non-metal. But the name of the non-metal, you should replace the last suffix of the non-metal using the prefix IDE. Yani replace the last 2-3 letters of the non-metal using the suffix or the prefix IDE. So oxygen, it will be oxide, nitrogen, nitride, bromine, bromide, chlorine, chloride, iodine, iodide, sulfur, sulfide, nitrogen, nitride, hydrogen, hydride, and so on. Phosphorus, phosphide, and so on. By practice, you can be familiar with these names. While the main group metals don't change the name, the metal is written as it is: sodium, calcium, magnesium, barium, etc. Don't change the name of the non-metal. That's it. Examples are here. KCl. Write the name of the K, which is the metal as it is. This is potassium. Write the name of the second element by replacing the end using, or the last 2-3 letters using the prefix IDE. This is chlorine, it will be chloride. So the full name is potassium chloride. MgBr2, this is magnesium bromide. CaO, this is calcium oxide. All these three examples belong to type 1 because here calcium, magnesium, and calcium all are from group A. All are group A metals. Type 3. In type 3 here, you should have a transition element, transition metal with non-metal. Transition metal with non-metal. The procedure of type 1 and type 2 is 90% similar, with a little bit, there is only one difference between them. What is this difference? To show you this difference, let me give you an example. Name the following. Let's say you have FeCl2 and FeCl3. As I mentioned, the procedure of type 1 and type 2 is similar, with one further step we need it here in type 2. So if we apply the procedure of type 1, we write the name of the metal as it is. This is Fe, this is iron, and here is iron. The name of the non-metal, replace the last suffix using IDE. So this is a chloride, and here is also chloride. As you see here, we ended with the same name for two different compounds. This is why the procedure of type 1 is not 100% fit with type 2. So we need a further step. What is this further step? The answer is writing. You should write the charge of the transition metal here using the Latin or the Roman numbers. As you know, Roman number 1 is I, 2 is double I, 3 is a triple I, and so on. Now the question is, how can we determine the charge of the transition metal here? How can we determine the value of the charge? If the metal is main group, we can easily determine it by using the previous method, which is the noble gas method. But as these are transition metals, we cannot apply the noble gas method to determine the charges. So you have to apply an alternative method. What is this method? Simply assume that the charge of the metal is X. Initially, I don't know the charge of the metal, so let's say the charge of this metal is X. Here, this is X. And here is also X. So you should determine the value of X, which is the charge of the metal. How can we determine it? Chlorine is a main group element. So we can determine its charge from the noble gas as we explained previously. Chlorine is 17, argon is 18. So chlorine should gain 1 electron to form Cl minus 1. And here the same thing. Chlorine is Cl minus 1. Now the total charge of these two molecules is 0. Both of them are neutral because we don't have any charge plus or minus written here. If nothing written here, as we said previously, then the charge is 0. Now, if you think about it in a logical way, you can conclude that the total charge of any compound equals the subcharges of its components. So here 0, this is the total charge of FeCl2. It must equal the charge of iron plus the charges of chlorine. Same thing for FeCl3. So the total charge of Fe plus 2, as we said, is 0. This equals the charge of iron. We assume that the charge of iron is X. So here is X. Plus the charges of chlorine. Again, here the total charge is 0. It equals the charge of iron, which is X, plus the charges of chlorine. This is Cl2. How many chlorine atoms we have? We have 2 chlorine atoms. Sorry. Here we have So here for this compound, to determine that we can think about it in a logical way, the total charge of any molecule equal the summation of all charges inside it. Here FeCl2, it has a total charge of 0, and we have 2 charges inside it. We have the charge of iron, which is X, and the charges of chlorine, which is -1 for each one of them. So the total charge, which is 0, by sense, it should equal the charge of iron, which is X, plus the charges of chlorine. We have 2 chlorine anions. Each one has a charge of -1. Now this is a simple equation. You can solve it in terms of X. So X, it will be +2, which means here we have the charge of iron in this compound is Fe plus 2. Do the same for the other. The total charge is 0 again. Here we have 1 iron atoms with X charge, and 3 with a charge of -1. So X is +3. Now to write the full name of each one of them, just write the charge of the metal in each one of them. So this will be iron. Here is iron using the Latin numbers. 3 is triple I. Sorry, this is 2. Chloride. And this is iron 3 chloride. This is how to name atoms or elements, compounds of type 2. Here we have some notes. For type 2, you should take these 2 notes into consideration. The first note is lead. If you have lead or tin, Pb or Sn. These are main group metals. When you go to periodic table, you will find them in group, they are group 1a elements, but they have similar properties compared to the transition metals, which means wherever you find them, you should deal with them like type 2. They are not related to type 1. Don't forget it. The second information is mercury. Mercury is a transition element. And in nature, in mercury, it has 2 naturally occurring ions, mercury 2, which is Hg plus 2, and mercury 1. We explained the formula of mercury 1 is Hg plus 1. But mercury 1, it doesn't occur in nature as monoatomic element, it's diatomic element. So wherever you deal with mercury 1, you should write this formula. It's Hg2 plus 2. Don't forget it. But you may ask why the charge is plus 2 and the name is mercury 1. Because here, as you see, we have 2 mercury atoms. Okay, the total charge is plus 2, but it's distributed among 2 mercury atoms, which means each one of them will carry a charge of plus 1. Let's take an example. Name the following. Hg2, let's say Br2. Here again, the mercury is a transition element. So to determine the charge, we'll assume initially that the charge is X. The charge is X. While bromine is a main group element, you can find the charge from corresponding noble gas. Following the previous procedure, you will find that the charge is -1. Here, the total charge of Hg2Br2, the total charge here is 0. So this is 0, equals the charges of mercuries. We have 2 mercury atoms, and each one of them has a charge of X, plus 2 bromine atoms. Each one has a charge of -1. When you solve it in terms of X, you will find that X is a plus 1. So this is, the name is mercury 1 bromide. Another example, let's say مثلا we have PbO2. PbO2. Lead, don't forget this exception. Lead is a main group metal, but it is similar to transition metals, which means you should deal with this as a type 2. This is as an exception. So the charge of lead is again X. This is X. Oxygen is main group. You can find the charge from the noble gas. It will be -1. Sorry, it's -2. So here the total charge is 0. The total charge is 0. It equals the charge of lead. We have 1 lead times X plus 2 oxygens times -2. So X, it will be plus 4, which means this is lead 4 IV. Sorry. This is IV oxide. Another example. This time, let's give you the name and ask you to write the formula. Give you the name, and I will give you the name, and we'll ask you to write the formula. So here, write the formula of let's say mercury 1 oxide. Mercury 1 oxide. Now we know that mercury 1, as we said previously, mercury 1 is not Hg plus 1. No, it's Hg 2 plus 2. Oxide from oxygen, so this is oxygen, and the oxide is the anion of oxygen, so it will be -2 from the corresponding noble gas. Oxygen 8, neon 10, so it will gain 2 electrons to form -2. Now the next step, as we have learned, is to make charge subscript. So this is Hg2. The new subscript is 2. Don't write Hg4. When you need, this is called polyatomic ions. Yani if the ion contains more than one atom together, and I need to change its subscript, don't multiply the subscripts by each other. You should use these brackets. So here, Hg2 all by 2. Did you understand how did we do it? Here, use the brackets. Don't write Hg4. This is wrong. And the oxygen, the new subscript of oxygen is 2. Now ask yourself, can we simplify this? The answer is yes. We can simplify 2 with 2 to end with Hg2O This is the formula of mercury 1 oxide. Last example, mercury 1, let's say chloride. Mercury 1 chloride. Mercury 1 again is Hg2 plus 2. Chloride from chlorine, from the corresponding noble gas, it will be minus 1. Now change the subscripts. This will go here, this will go there to form Hg2. The new subscript is 1, so it will remain as it is, while Cl it will be 2. Can you simplify it? Now, theoretically, yes, we can simplify it, but if you simplify it, you will end with HgCl, and as you see, this is mercury 1, and I wrote mercury 1 as a monoatomic element, which is not allowed. So here in this case, even though we can theoretically simplify 2 and 2, but you should keep it as it is, because mercury 1 is always a diatomic, 2 mercury atoms together. I hope it's clear. Now let's proceed to the third type. This is type 3. Type 3, in which you have a polyatomic ions, metal with polyatomic ion. Polyatomic ions, from the name, poly means more than one. Atomic ions, yani we can understand that these ions consist of more than one atom. 2, 3, 4 atoms together with a certain charge, positive or negative. Actually, there is no way to explain how these to explain the names of these polyatomic ions. So you should memorize them from this table. This is very, very important table. You should memorize all polyatomic ions listed in the table. You should memorize everything. The formula, the name, and the charge. Yani when we say ammonium directly, it will be NH4 plus 1. Acetate, CH3COO minus 1. Cyanide, Cn minus 1. Hydroxide, OH minus 1. Sometimes the difference between them is one letter only, like nitrate and nitrite. Can you see them here? Nitrate and nitrite. Nitrite is NO2 minus 1, while nitrate is NO3 minus 1. Nitrate, nitrite. So one letter is the difference. So you should be precise and accurate. Memorize them. Now, believe me, once you memorize them, all questions related to this type, it will be straightforward. 1 plus 1 equals 2. Why? Because the procedure is very easy. In type 3, write the name of the metal as it is, and write the name of the polyatomic ion as it is. That's it. Here we have some examples. NaOH. This is type 3. We have a metal which is sodium. OH from the table, here is the table, here is OH, can you see it? OH is here. This is the name of OH is hydroxide. So Na, write the name of the metal as it is. This is sodium. The name of the non-metal as it is hydroxide, so it will be sodium hydroxide. MgNO3 by 2. Mg is magnesium, NO3 is nitrate, so this is magnesium nitrate. NH4 by 2 SO4, NH4 from the table is ammonium, SO4 is sulfate, so this is ammonium sulfate. This is how to name type 3. Very simple, very easy, but you should memorize the names of these polyatomic ions. After that, everything else will be easy. Let's give you a third example, this time using a transition element with a polyatomic ion. Name the following. Let's say FeSO4. Because iron is a type 2 element, then we should determine its charge. Use the previous procedure. Assume the charge of iron is X. SO4, this is a polyatomic ion. As we said, you should know the ions. You should know, sorry, the charges of these polyatomic ions. It's here. Can you see the last one? The charge is minus 2. So the charge of this is minus 2. Now we can solve it. 0 is the total charge. We have 1 iron with a charge of X, and we have 1 sulfate with a charge of -2. So when you solve it, you will find that this is -2, then X is +2. So the name of this compound is iron 2 sulfate. Another example, let's say Ba3 PO4 by 2. Sorry, barium is a many group, so no, let's change it to iron again. Fe3 PO4 by 2. Because iron is a transition, so the charge is X, while here the charge is -2. Here the charge is -2. Total zero, the total charge is 0. We have 3 irons. Each one has a charge of X, so this is 3 times X plus. How many phosphate anions do we have in this compound? The answer is 2, because inside the bracket is PO4, 1 unit of PO4. Outside is 2. So we have 2 PO4 units, and each one of them has a charge of -3, not -2. Okay. From the table, this is -3. 2 times -3. When you solve it, you will find that X is +2. So the name of this compound is iron 2 phosphate. Iron 2 phosphate. Iron 2 phosphate. The last type of these of the naming part is type 4. This is type 4. Type 4. In type 4, as we said, you should have a nonmetal with another nonmetal. It's similar to type 1 with a difference, one difference between them. The difference is the subscripts. In type 1, the subscripts were not written in the name, while here in type 4, you should write the names of these subscripts using the Greek numbers, the Greek prefixes. So 1, if the subscript is 1, you should write mono, 2 di, 3 tri, 4 tetra, 5 penta, hexa, hepta, octa, nona, and deca. So this is the difference. Here we have to take into consideration one important detail, which is the mono. Now, if the subscript is 1, sometimes you should write mono, sometimes you should not. While if the subscript is 2 or more, in all cases you should write di, tri, tetra, penta, hexa, hepta. We don't have a problem if the subscript is more than 1. The problem is when the subscript is 1, because there are different cases. Some cases, again, you should write one mono. In other cases, you should not. So here we wrote cases of mono. What are the different cases of mono? The first point is mono is not written for the first element at all. So if the subscript of the first element is 1, don't write mono for the first element. So CO2, in CO2, the subscript of carbon is 1. We don't write monocarbon. This is carbon, not monocarbon. While for oxygen is 2, 2 is written. So this is carbon dioxide. Dioxide. This is what I mean by the first point. The second point, write mono for the second element if the formula is AXB where X doesn't equal 1. If X equals 1, then don't write mono. What I mean by that? Now here is A, and here is B. We agreed that the subscript if the subscript of the first element is 1, we don't write mono. So here this is A, not mono A. Now the subscript of the second element, which is B, is also 1. If the first and the second is 1, both of them is 1, then we don't write mono for the first or the second. While if A is 2 or 3 or 4 or whatever, and B is 1, in this case you should write mono for the second element. Here we gave you example, A1, B1, we don't write mono for A or B. A2, B1, write mono for B because A is not 1. AB2, we don't write mono for A because it's the first element, so according to the first point, 1 is not written for the first element at all. The last case, if the second element is oxygen with a subscript of 1, then always you should write monoxide. So this is an exception. So AO, even though the subscript of the first and the second 1 and 1, which means we don't need to write mono for the first or the second, but because the second element is oxygen, always write monoxide if its subscript is 1. For example, when we say CO, the subscript is 1, so this is carbon monoxide. Carbon monoxide, and so on. Here we have some examples. CO2, carbon dioxide. SF6, this is sulfur, not monosulfur. According to the point 1, mono is not written if the subscript of the first element is 1. We don't write mono at all. So this is sulfur, hexa from 6 from the table, hexafluoride. N2O4, 2 is di, so this is di, nitrogen, 4 is tetra oxide, di-nitrogen tetraoxide. Here we have more examples. CO2, this is carbon dioxide, CO, carbon monoxide, don't forget the last exception. SO2, sulfur dioxide, SO3, sulfur trioxide, because 3. NO2, N is nitrogen, 2 is di, O is oxide, so this is di-nitrogen dioxide, NO, nitrogen monoxide, N2O5, this is di-nitrogen pentaoxide, NF3, nitrogen trifluoride, Cl2, look, Cl here, it came as the first element. So don't use the prefix IDE. IDE is written when the element is the second element. But the rule states that if for the first element, you should write the full name. So the full name of Cl is chlorine. As we have 2 chlorine atoms, so this is dichlorine, not dichloride. Please, don't forget it. So this is dichlorine. 5 is penta. O is oxide, so this is dichlorine pentaoxide. Here you have more examples. You can solve them, and I hope everything is clear. Thank you so much.